Okay, autonomous differential equations are equations where we only have our dependent variable appear anywhere in the equation. So we got y prime is totally just a function of y. So y prime is some function that only explicitly depends on y. There are no x's anywhere. Now, a lot of times these are very hard to solve in general. So what we just try to do is sketch out what possible solutions might look like with a slope field. So I can go to a slope field generator here and type in y squared minus 4 is y prime. And here you're looking at the slope field. And I want you to notice that some interesting stuff seems to be happening at a couple of lines here. We'll call those equilibrium solutions. Equilibrium solutions happen when y prime is equal to 0. Well, for autonomous DEs, a lot of times we can solve those for y, and we get horizontal lines. So we get y squared minus 4 equals 0. That will make y prime equal to 0. So what do we get? We get y squared equals 4, so y is plus or minus 2. So I've got two solutions here, y equals negative 2 and y equals 2. What's his derivative? What's the derivative of a line? 0. So these are solutions to the DE. There are an infinite number of solutions, remember. I'm not saying every solution is going to have this form, but these are two solutions to that DE. The horizontal lines, y equals negative 2, kind of missed there, and y equals 2. Now, what we care about these is, are these stable or unstable equilibrium solutions? Meaning, if I'm on a solution curve that's near y equals 2, is that solution curve going to get closer and closer to this equilibrium solution or further away? So if we look at our slope field generator here, if I'm actually on the line y equals 2, if my y value actually equals 2, and you can see I'm kind of close there, there's my y value. On any solution curve, that's what we're looking at. These are all different solution curves here. Any solution curve where y actually equals 2, I'm stuck. Y is always going to equal 2 on that curve. Similarly, if my curve passes through y equals negative 2, then that's an equilibrium solution. That's a solution, y equals negative 2. But what if my y value is, excuse me, negative 1.59? Then this is a solution curve that never actually hits y equals negative 2, but you can see it's getting closer and closer to it. Or if I'm down here below, if I'm on this curve, if say I solved an initial value problem when x is negative 4.21, y is negative 2.61, then this is the curve that passes through that point that satisfies that differential equation. And you can see it's approaching that equilibrium curve. But if I'm close to this one, if I'm on this curve, if that were my initial value right there when x is negative 2.82, y is 1.97, I'm running away from y equals positive 2. This curve is being repelled by this guy. So that means what we would say is that this curve here is an attractor. This equilibrium solution here is a repeller. And the way we figure all this out is by doing a sign chart. So we do a sign chart around these equilibrium solutions, and we're doing this for y. This is a lot like what you did in Calc 1 when you were doing sign charts for the derivative, you need to find the shape of the graph. It's very similar, but now we're looking at y's instead of x's. So everything's going to be vertical instead of horizontal. Okay, so what I care about is the sign of my derivative. Are my little slopes going to be positive or negative? That's all I care about. And we could just pick test points, for example. Say I pick a test point of 3. I'm over here in this region. 3 squared is 9. 9 minus 4 is 5. It's positive. So y prime will be positive in this region. Or the way I like to do sign charts, put in all of my linear factors here on the side and do these one at a time. Y plus 2 in this region below -2 will be negative, and then it switches to positive. Y plus 2 equals 0 at -2, so below that it's negative, and above it it's positive. Y minus 2 switches signs at 2, so he's negative below and positive above. Two negatives, those are multiplied together, make a positive and a negative makes a negative, and a positive. So back here below, remember, we're thinking vertically now. This is weird compared to what you did in Calc 2 or Calc 1. This is a little weird. We're looking vertically. All of my slopes down here below -2, all my slopes are positive. So if I just sketch in some of those slopes, in this region between -2 and 2, all my slopes are negative. That's the x-axis there. And up here, all my slopes are positive again. So any solution near this guy will run away from him. Any solution near this guy will be attracted to him. So we say this guy is an attractor or a stable equilibrium. This guy here is a repeller, and he's an unstable equilibrium. I like to think stable and unstable. Think about a ball. If I've got a ball in a little valley here and I give it a little nudge, it will roll back down to the bottom. That's an equilibrium point, because if I just walk away, the ball will stay there. And if I give it a little nudge, it will come back. The universe will force it back toward that equilibrium point. This is stable. But if I have a ball sitting on top of a hill, and right now it's just sitting there, if I walk away, it stays there. It's an equilibrium. It's not going to move on its own. But if I give it a little nudge, it's going to roll away. It won't come back up the hill. This is unstable. Okay, so maybe one more quick example. Maybe we have y prime equals y squared minus 7x plus 12. And we want to find and categorize the equilibrium solutions. So we would set y prime equal to 0. So y squared minus 7x plus 12 equals 0. That factors. Now, you're going to get confused when you're doing these. You might look at this and think like homogeneous with constant coefficients. Remember characteristic polynomial, all that stuff. These are completely different. These are not those problems. Those were y double prime. There's no x anywhere. I apologize. That is not an x. You get used to writing x. That's a y. The homogeneous with constant coefficients, those were y double prime minus 7y prime plus 12y. It's a completely different problem. I know it looks similar. It's not what's going on here. We want to know, where does y prime, this, equal 0? And this guy's going to factor, that's y minus 3, y minus 4. And we get two equilibrium solutions, y equals 3 and y equals 4. And then we would, those are both horizontal lines. And now we want to make a sign chart for y prime. You know, something I never do. Let's draw this vertically. Now that would confuse me writing it out like that. I'm not gonna draw it vertically. Like we always write our sign charts horizontally. No, really, like I could just do plug and chug. I could pick a test point, pick any point back here below 3, 1, and plug it into the DE. 1 squared minus 7 times 1 plus 12. So what do we get? 1 minus 7 plus 12 is positive. Pick any number between 3 and 4. See, here's where I don't want to go through that work. 3.5 squared minus 7 times 3.5. I don't want to go through that work. I'm lazy, but we could. All I care about is when I plug in 3.5, do I get a positive or a negative? I'm going to use the linear factors to do that. Y minus 3, y minus 4. And I'm going to build this little grid here. And I'm going to do these one at a time because this is what y prime is. It's these two guys multiplied together. He individually, you do one row at a time. He changes signs at 3. Anything below 3 minus 3, you get a negative. Anything above 3, you get a positive. Try it. Plug in any number bigger than 3 here for y, you'll get a positive. He's going to switch here at 4. And he's negative below and positive above. Try it. Plug in any number less than 4. Minus 4, you get a negative number. Above 4, you get a positive. Now just multiply up. 2 negatives make a positive. 1 negative is negative. 2 positives is positive. So that means below 3. So remember, this is weird. I'm thinking vertically here. All of my slopes are going to be positive from left to right. In between 3 and 4, they're all negative. And above 4, they're all positive again. Okay, so now we notice that from both sides here, we're approaching 3. So he is a stable equilibrium. From both sides here around 4, we're running away from 4, so he's unstable. And you're going to have a question on the final, just like this. Stop this one.